In our last video, we discussed how to use the method called substitution to find a common solution to a linear system when they did not provide us with a graph. Substitution is a great method to find a common solution, but often there are situations where a second method, elimination, would actually prove to be more efficient or easier and quicker to use in order to find the correct answer. We're going to show you an example of a problem where I would prefer to use elimination as my method of choice instead of substitution to get to the common solution. Let's first discuss why this equation, 2x minus 3y equals 15, and this second equation, 4x plus 3y equals 3, are two equations in a linear system that makes more sense to use elimination. If you'll recall, for substitution, we need one of the equations to tell us y equals something or x equals something. We can see for both of these equations that they are not solved for x or solved for y. A second thing I can see is that both of these equations have a positive 3y in one and a negative 3y in the other. I realize that these are inverses, and if I were to add both equations together, a positive 3y and a negative 3y would eliminate each other and get rid of the y's from the equations entirely. So adding these two equations together, I can only combine like terms. I can combine anything in the left expression for the blue equation with the left expression in the red equation if they are like terms, or the 2x and the 4x could be combined together, and then they would provide us with 6x. The key thing we noticed earlier, when I combine this positive 3y with a negative 3y, they will eliminate or wipe each other out entirely. I'll bring the equal sign down, and the right expressions for both equations were added as well. All we do is add 15 plus 3, and we get to 18 at that point. We can now see why elimination was an attractive method to use here. Very quickly, with one step, we eliminated the y's from our linear system, and we got ourselves a new equation that has only x's in it. A simple equation that one step later, after we divide both sides of this equation by 6, we find that x is going to be equal to 3. Once I know that x is equal to 3, I can then use that information, plug it into either equation that we started with, and figure out what the y needs to be. So if I take this first blue equation, 2x minus 3y equals 15, and I replace the x with 3, I now have an equation that could be solved for y. 2 times 3 provides us with 6 minus 3y equal to 15. And at that point, I would subtract 6 from both sides. Which would provide us with negative 3y, which is equal to 15 minus 6, or 9. I could divide both sides by negative 3 and realize that y must equal negative 3 here, then x equals 3. One final point, if I'm going to take this positive 3 for x and this negative 3 for y, I already know they work in the blue equation, but they would also need to work in the red equation to truly be the common solution. A great way to check if I'm correct after doing these many steps is to plug in the positive 3 for x, the negative 3 for y into that other red equation, and then to see if that'll actually work. So I replace my x with 3, I replace my y with negative 3, and now I follow order of operations at this point. 4 times 3 is going to give us 12, plus a 3 times a negative 3 gives us plus negative 9. That's equal to 3. And if I do 12 plus negative 9, I do get to 3. Now the fact that this was a true statement proves that this was a solution to both of my equations.